Hello everyone. So in this session, we'll dive deeper into linear algebra concepts that are crucial for data science and machine learning. Specifically, we'll focus on matrices, their understanding, what they are, how they are shaped, and the fundamental operations that you will be performing on them, including addition, subtraction, multiplication, and matrix multiplications. We'll also highlight special matrices like identity matrix, zero matrix, diagonal matrices, and showcase how each of them will be used in practice. After that, we'll move on to the determinants and inverses, uncovering why the determinant tells us about the scale or collapse of space and what it means when it's zero. We'll also see how to determine if a matrix has an inverse, why singular versus non-singular matrices matter, and how this directly ties into machine learning algorithms, especially linear regression and solving system of linear equations. We'll also be walking through hands-on demonstrations in Python using NumPy to illustrate all these concepts using simple numerical examples. Let's get started. So let's first import NumPy. Okay, so matrix, as we have already seen, is a grid of numbers. You have rows and columns. So this is a matrix with the dimensionality m rows and n columns. Okay, so the shape of this matrix is m cross n. Now let's have a look into the concept of row vectors and column vectors. So as you see in this matrix, each column will be referred as a column vector. Okay, so you have n number of column vectors. Okay, so each column, so here if you see the definition, all the data points are exactly in one column. Okay, all the data points are exactly in one column. In the case of a row vector, okay, all the data points are exactly in one row. Okay, so essentially these are all row vectors. So these are all row vectors. Okay. Now you might think mathematically row vectors and column vectors are one-dimensional arrays. Yes, indeed, mathematically they are one-dimensional arrays. Okay, but in Python we have to represent them with two dimensions. Okay, here I am creating a NumPy array. So if you look closely, there are two square brackets for opening and two square brackets for the final closing. So that two square brackets directly indicate that we are going to create a two-dimensional array. Okay, so the first row contains the numbers 1, 2 and 3, and then the next row contains the numbers 4, 5 and 6. So very well, this is actually a two-dimensional object that we have created with the shape 2 rows and 3 columns. That's very clearly observed here. So now if you extract a row from this, that will also be two-dimensional. Okay, let me create a new row vector from scratch. So again, since I have opened two square brackets and closing again two square brackets, the array that I'm going to create essentially will be two-dimensional once again. Okay, so I'm getting a row vector as 10, 20 and 30. So all the numbers are in exactly one row. So the shape is one row and 3 columns. So all the numbers are in one row, and the number of columns will be equal to the number of numbers in that row vector. Okay, so similarly, again I am creating a column vector by opening two square brackets and finally closing it by two square brackets, which means again I am going to create a two-dimensional object. Okay, so all the numbers are again in one column, so that makes it a column vector. So if you have a one-dimensional array, for example, let me have a simple array as np.array with a single square bracket open and close, some numbers, let's say 10, 20, 50. Okay, let's see this array and let me show you the shape of this array. So this displays 3 comma nothing. So this is technically one-dimensional for NumPy, okay, because the second dimension is not present. A row vector has got the second dimensions. Okay, so one row, 3 columns. A column vector also has the second dimensions, 3 comma 1 in this case. Okay, but a normal one-dimensional array in NumPy, okay, this is one-dimensional. This doesn't have the distinction of a row vector or a column vector because it doesn't have the second dimensions. Okay, that's what I said some time back, that in Python and NumPy, okay, one-dimensional array might sometimes behave like a row vector, but it's actually not a row vector. They are supposed to be created as two-dimensional as we did. Great. So now let's see some common matrix operations. Fine. So I've got my matrix again here. So matrix A is defined by A11, A12, A13 in the rows, and then again A21, A22, A23 in the next row, and so on. In the last row, I have AM1, AM2, AM3, and so on. Similarly, my B array has B11, B12, B13, B21, B22, B33, and so on. So when I am adding A and B matrix, I have to first make sure that the shapes of A and B are exactly same. Okay. So if A contains, let's say, numbers 1, 2, and 3, 4, 5, and 6, and B contains, let's say, 10, 20, 30, and this is 40, 50, and 60. Okay, the first element of A will be added with the first element of B. So matrix addition and subtraction, okay, are element wise operations. So when I do A plus B, the first element of A gets added with the first element of B, and that's how you get the first element in the net matrix as 11. Then the second element gets added with this, so this becomes 22. 3 gets added to 30, so this becomes 33. 4 gets added to 40, so this becomes 44. 5 gets added to 50, so this becomes 55. And 6 gets added to the 60, so this becomes 66. Super. So similarly, if I have B minus A, then how does it go? So in this case, the first element of B, okay, minus first element of A. So the first element of A gets subtracted from the first element of B. So that is 10 minus 1, which is 9. So 10 minus 1, which is 9. And then this is 20 minus 2, which is 18. This is 30 minus 3, which is 27, and so on. Okay, that's how again it goes, element wise subtraction, which clearly means that you can add or subtract the matrices only if the dimensions are exactly the same. If A or B contains additional rows or columns, then the matrix addition or subtraction operations will fail. So let's see the same in terms of a Python code. I've got my matrix A and B. So 1, 2, 3, 4, 5, 6, and this is again 10, 20, 30, 40, 50, 60. So this is the result of A and B, and this is the result of A minus B. Okay. Now in the case of scalar multiplication, you are multiplying a single number with a matrix. So that single number gets broadcasted. Okay. So this is a concept of broadcasting which is supported in NumPy. Okay. So what is happening? So let's say you want to multiply 10 with a matrix as 1, 2, 3, 4, 5, 6. So this is done in this manner. Okay, so the same 10 gets broadcasted to each element of this matrix. Okay, so 10, 10, 10, then again. So internally a new matrix gets created which has exactly the same shape as that of your original matrix, let's say, which you wanted to multiply. So let's say this is A and this is some constant C. So C internally becomes this. A still remains the same as 1, 2, 3, 4, 5, and 6. And now the element wise multiplication. So scalar multiplication is always element wise. Remember this. Element wise. Okay, which means now this 10 gets multiplied by this 1. So the resultant would be 10. This 10 gets multiplied by 2. So this is 20. This 10 gets multiplied by 3. So that is 30, and so on. This is 40, 50, and 60. That's your final product. Okay. That's how the C into A works. So this 10 essentially gets broadcasted to each element of A for the multiplication to happen. That's exactly the concept of broadcasting. So here I've got my matrix 1, 2, 3, 4, and that is multiplied by a scalar 3. So 3 gets multiplied to each of the elements, and this is what I get. This is a proper matrix multiplication defined mathematically, where a very important constraint needs to be followed. So you can do proper matrix multiplication only and only if the inner dimensions match. So suppose you want to multiply A and B. Okay, both are matrices. So some rows and some columns. Okay, so this is M cross N, B is N cross P. If you notice here, B has to be having same number of rows as the number of columns in A. So this is what we call as inner dimensions. So for matrix multiplication to be successful, the inner dimensions must match. Okay, so inner dimensions means the number of columns in A should match exactly the number of rows in B. So if you want to multiply B and C, so let's say B is P cross Q matrix and C has to be Q cross something, maybe M, because again this Q has to be same as this Q. right? So if C happens to be anything, let's say M cross N, okay, then the number of columns in B does not match with the number of rows in C, so that matrix multiplication will again fail. So I hope you understood this. Okay, so let's have a look at what happens in this case when you have A as 1, 2, 3, 4 and B as 5, 6, 7, 8. So this is A and this is B, okay. So as we said, the number of columns in A has to match with the number of rows in B. Why? So what happens is this gets multiplied by 5, okay, and this 2 gets multiplied with 7, okay. So that's what you see, 1 into 5 and 2 into 7, right? So that will give the first element of the product. The next element is again 1 is multiplied by 6 and 2 gets multiplied by 8, okay, and then this 3 gets multiplied by 5 and 4 gets multiplied by 7, that's this, and finally 3 gets multiplied by 6 and 4 gets multiplied by 8, that's the last element, okay. So that's how you get this 46. So the product of A and B is basically matrix 19, 22, 39, 46, and these are the individual calculations, okay. Now just imagine you have one more row here. So B is not 5, 6, 7, 8. Let's say B is 5, 6, 7, 8, 9 and 10. This is your entire B. In this case, 1 gets multiplied by 5, 2 gets multiplied by 7, but there is nothing to multiply with this 9, and that's where the multiplication actually fails, okay. So you have to make sure the number of columns in A has to be equal to the number of rows in B, right? Yeah, so the same thing in terms of Python code. You will be using this function called as dot. So A comma B, so np dot dot A comma B is same as the matrix multiplication of A and B. So you can see the numbers are very well the same what we got by manual calculation. And you can also use this operator at the rate to multiply A and B. Now remember that A multiplied B is not same as B multiplied by A, okay. We can prove this. So let's say we have B at the rate A. Let's see what is the result. You can see the answer is completely different. This is 1922, 4350. This is 23, 34, 31 and 46. So this is completely different, okay. Here we are checking whether all the elements of this C alt is same as all the elements of this C. Essentially, I am just checking whether these two matrices contain exactly the same elements, okay. There can be small differences in terms of floating point approximations, but more or less all the numbers are close to each other, that's what. So since there is no error, means the result that you get by using the np dot dot function and the result that you get by using the at the rate operator, they are all same. Now there are some special matrices defined in NumPy. So we can start with an identity matrix. So identity matrix is a matrix which contains all the elements as zeros except for the main diagonal, which contains only ones. So if you see here, the main diagonal contains only one, okay. These are all one, rest all the elements have to be 0. That's the identity matrix. So what is the main property of the identity matrix? If you multiply any matrix with the identity matrix, you will get the same matrix, okay. So we can verify this. So I am creating an identity matrix of 3 cross 3, and I've got my original matrix as 1, 2, 3, 4, 5, 6, 7, 8, 9, and let me multiply this 3 cross 3 matrix with an identity matrix of the same shape. So you can see even after multiplication with the identity matrix, the numbers are very well the same. It's only that the original matrix contains integers, and after matrix multiplication, the same numbers have been converted into float. Zero matrix is a matrix which contains only zeros, typically used for pre-initialization, memory pre-allocation you can say, or you want to create a matrix beforehand, and then you want to update the elements of that matrix within a for loop or something. So for memory pre-allocation, you can use this zeros matrix where all the elements are technically zeros. So you can use the function np.zeros, and the dimensionality of that is specified as a tuple. So 2 rows and 3 columns. This will give me a matrix of zeros which contains 2 rows and 3 columns. So this 2 is for the rows and 3 is for the columns. And if you want a multi-dimensional, then you can make it, let's say 2, 3, 2. Then this will become 2 planes, 3 rows and again 3 columns. Okay. So this is 2 planes. So plane 1, plane 2. So this 2 becomes the number of planes. Then this 3 becomes the number of rows, and then this becomes the number of columns. We can verify that. I'm just changing it to 4. So now you can still see 2 planes, okay, and first plane contains 3 rows and 4 columns, and the second plane will also contain 3 rows and 4 columns. So this is plane 1 and plane 2. So you can actually go multidimensional as well if you want. Diagonal matrix is a matrix where all the elements are zeros again, except for the main diagonal, they will be non-zero. And you can very well see that the identity matrix is a special case of a diagonal matrix where all the diagonal elements, main diagonal elements, are actually 1. You can actually create a diagonal matrix by specifying an array of numbers. So these numbers will become the main diagonal elements, rest all elements will become 0. Okay. So here we are creating a diagonal matrix. Okay. So I have an array, a simple Python list will also do, or a NumPy array. So 10, 20, 30. So NumPy creates a diagonal matrix with these numbers in the main diagonal, rest all elements are 0. And if you already have a square matrix, okay, you can use the DIAG function again to extract the main diagonal elements. Okay, so main diagonal is again 159. So this is my main diagonal. Okay, and this is called as anti-diagonal 753. This is anti-diagonal. So in mathematics, we do not have much applications of anti-diagonal elements, so we do not have a straightforward function to extract the anti-diagonal elements. So when you flip the matrix up, down, or left, right, basically the main diagonal becomes the anti-diagonal and the anti-diagonal becomes the main diagonal, and then you can extract. So here is a quick summary of all the Python functions which we have learned so far. We have seen how do we create matrices, how can we get the shape and dimensionality of the matrix multiplications, and also we have seen some of these special matrices. Okay. Now, what are the use cases? We have been seeing matrices representing the entire data sets where the rows will be referred as the samples and the columns are nothing but the attributes or the features. Okay. We often use matrices for transformations like rotation or scaling operations, linear, nonlinear operations, and then in neural networks the weight matrices will be there. This will be multiplied by your input vectors or activation functions, and that is how the neural network will give outputs, and during the backpropagation the weight matrices will be updated by using some sort of a variant of gradient descent. So in linear regression again, in the previous video we have seen that your model can be expressed by x beta, and the optimal values of these beta coefficients are again obtained by some matrix transformations. So let me create a matrix with random numbers. These are some special matrices once again. So here I am specifying 3 rows and 2 columns. So I have got matrix with 3 rows and 2 columns. You can see it's having a shape of 3, 2 and dimensionality of 2. Similarly, I can have another matrix with 2 rows and 4 columns. So 2 rows and 4 columns. And I can multiply them. So this has a shape of 3 cross 2. This has a shape of 2 cross 4. Okay. So the matrix multiplication will be successful. So this is 3 cross 2 and the other one is 2 cross 4. So the inner dimensions are matching, and so the product will have the outer dimensions. So 3 cross 4 is the dimensions of the product. Okay, so let's see some of the broadcasting pitfalls. So as we have already seen, the element-wise operations need the exact shape of the matrices must be same. Similarly, for matrix multiplication, the inner dimensions must match. So what if I have got a matrix which is having a shape of 2 cross 3, and if I try to multiply that with 2 cross 2, you can see that the inner dimensions are not matching. This is 3 and this is 2. So I'll get an error in this case. I'm trying to catch that error and print it here. Okay, let's see what is the error I get. So it gives me a matrix multiplication error, matmul, operand 1 has a mismatch in its core dimension 0, and so on. So basically what it is saying is 2 is different from 3, right? So this 2 is being matched with this 3. So it was expected that this and this would be same, okay, which is not happening here. Similarly, for the addition again, as I said, addition is a element-wise operation. So again, the shape must match exactly. So 2 comma 3 is not same as 2 comma 2. So again, the addition operation is failing. Okay, so there is a problem in broadcasting. So 2 comma 3 cannot be broadcasted to 2 comma 2. That's the error. So please check the shape of your matrices before performing these operations, else you will be getting these kind of errors. So in this notebook, we'll have a look into the key matrix properties and applications. So we'll start with the determinants and matrices in this notebook first. So let me import NumPy. So what is a determinant then? So determinant of a square matrix, n cross n or m cross n matrix, is a very special value, and that can be interpreted in many ways. So two of the most common interpretations for determinants are it can be seen as a scaling factor when you are using this matrix as a transformer matrix. So when you multiply another matrix with this matrix, the other matrix will get scaled based on the determinant of this matrix. Okay, so this can be seen as a scaling factor for any transformation that you carry out using this matrix in the n-dimensional feature space. Now, if this matrix happens to be a 2D matrix, for example, a 2 cross 2 shape matrix, then you are essentially scaling a area. And for a 3-dimensional matrix, this can be seen as a volume scaling. Okay. So let's say my matrix is ABCD. It's a 2 by 2 matrix. So the determinant is formally given by the product of AD minus CB. Okay. So AD minus BC, that's the simple way you can calculate the determinant of A. For bigger matrices, the formulas are slightly more complex, which I'm skipping in the discussion. So good thing is, however big that matrix A might be, we'll be using the NumPy functions to calculate the determinants if it is feasible. Okay. So when is it feasible then? So there could be a scenario where your matrix A is not invertible. Okay. So not invertible means the inverse of this matrix A does not exist. So when does that happen? When the determinant of A is equal to 0. Basically that entire 2-dimensional feature space has been scaled or shrunk to nothing. Okay, that collapses to a lower dimension, maybe a line or maybe a point. Okay, so whenever the scaling of that matrix collapses, okay, that is where the determinant of that matrix goes to 0. Okay, so in simple terms, if the determinant of this matrix A is 0 or close to 0, then this matrix becomes a singular matrix, and singular matrices cannot be inverted. So the inverse of this matrix does not exist. So let's calculate this in Python. So I'm going to use the linear algebra module of the NumPy library, and the function is called as determinant. So I'm defining my matrix A and passing it to the determinant function in linear algebra module. You can see the determinant of the matrix is minus 2 point something zeros, and finally I've got this 4. So basically this is a small floating point error that is an artifact of converting these floating point numbers into binary, because all the computers do all the calculations in terms of binary. So all these calculations that AB minus AD minus BC, that calculation that we had seen here, this is actually done in binary, okay, in zeros and ones. And the result is again converted back into a decimal notation. So conversion of decimal into binary, all the calculations in binary, and then conversion of the output back into the floating point, that introduces some errors. Okay. So these zeros that you are seeing, 15 zeros followed by a 4, that's just an artifact of the loss of precision which is resulting because of all these floating point to binary conversions. Okay. So technically this is insignificant. Your answer is still minus 2. Okay. And that you can very easily see by doing it manually. So I have done that here. So 1 times 4 minus 2 times 3. It is as simple as that. So that is 4 minus 6, which is minus 2. So manually you are supposed to get minus 2, and do not interpret this as minus 2.15 zeros and then 4. These 15 zeros are insignificant. This is still minus 2. Okay. Another important thing here is we have a negative sign which introduces a flip or the orientation change in 2D. So basically you are not just scaling it by a factor of 2, but you are also flipping that. Okay. So 2 is the factor by which the areas are scaled, and also you are flipping that. So there is one more example here. I've got a 3 cross 3 matrix, and let's see the determinant. Again, the determinant was supposed to be 3, but again this is not exactly 3. This is again an artifact of floating point, loss of floating point precision during these calculations. Okay, so this is approximately 3 ultimately. So as again, if the determinant is close to 0, the matrix will be seen as a singular matrix whose inverse does not exist. Okay, if the determinant is not 0, then it is a non-singular matrix. As simple as that. So what are matrix inverses then? Okay, so I'm defining inverse of a matrix as A to the power of minus 1, such that if I multiply that inverse with the original matrix, so this is the matrix inverse. If I multiply that with the original matrix, I'm supposed to get the identity matrix. It doesn't matter in what order you are multiplying, either before or after, because if A is a square matrix, then its inverse will also be a square. Okay, so you can multiply the inverse before or after. In both the cases, you end up with the identity matrix. What is an identity matrix? Where the main diagonals are ones, rest all the elements are supposed to be zeros. So in this case, if it is a 3 cross 3 matrix, then your identity matrix will also be 3 cross 3. There is a straightforward Python function that I'm going to use to calculate the matrix inverse. So this is my matrix 1, 2, 3, 4, and the inverse of the matrix is given here. And we can verify that this is the right inverse. How do we verify? We'll just multiply this inverse with the original matrix and see whether we are getting an identity matrix or not. Okay, so I don't see exactly 1 0 and 0 1. I again see something. So this was supposed to be 1 0 and 0 1. Let's look closely. Something to the power of minus 16. So that's technically again very close to 0. Okay, so you are getting close to the floating point precision of numpy, which is 10 to the power of minus 16. So what I'm trying to say is numpy cannot differentiate two numbers if the difference between the numbers is less than 10 to the power of minus 16. Okay, so any number which is close to 10 to the power of minus 15, minus 16, or even lower, they are technically interpreted as zeros. Okay, this is anyway 1 and this is anyway 0. Okay, so this is approximately 0 only. Okay, let's take another example here. I've got my 3 cross 3 matrix. The determinant is non-zero, so definitely I should be able to get the inverse of it. So I'm able to get the inverse, and you can see. If you closely see, there might be again numbers in that range, 10 to the power of minus 14, 15 or 16. These are practically zeros. So you can very well replace these numbers with zeros. Okay, so this is 0. Now rest all are anyway. So this is 1, this is 1, this is 1, this is 0, this is 0, this is almost 0, this is almost 0. This is anyway 0 and this is 0 and 0. So again you can see that the matrix A multiplied by its inverse is actually equal to the identity matrix, right? So we have verified by taking a 2 cross 2 matrix as well as a 3 cross 3 matrix, and it is always going to follow that property. So if the determinant of matrix is not equal to 0, it's non-singular and its inverse will exist. And if the determinant is equal to 0 or very close to 0, then it is a singular matrix and the matrix inverse does not exist. Now, where do we encounter such scenarios? Okay, so if you have heard about the multicollinearity problem, so multicollinearity means, let's say if you have a data set with features x1, x2, x3 and so on, p number of features. Okay, now each feature would be a column vector. Now imagine that x3 somehow is a linear combination of x1 and x2, or basically you can also think that x3 is just a product of x1 and x2, or addition of x1 and x2, or maybe the ratio of x1 and anything that you can directly derive using some other columns. Okay, so essentially then this becomes a derived feature. There is no unique information contained within x3 because the information is derived from x1 and x2. In such case, this x3 will have a high degree of correlation with x1 and x2, and that will lead to multicollinearity. So if there is only one such feature, then it may still be okay. But if there are several such features which are linear combination of the other features, or maybe some scaled version of the other features, okay, then lot of correlated features will lead to a problem called as multicollinearity. Okay, I repeat, lot of correlated features. If the correlation coefficient exceeds 0.9 especially, okay, the Pearson correlation coefficient exceeding 0.9 directly indicates that your data set suffers from a problem called as multicollinearity. So in that case, the determinant of such a matrix will be close to 0, and such case cannot be solved for linear regression. Now the question is why? So if you look into the formula that we discussed in the last video, so the normal equation that you use to solve the linear regression problem, so this beta, so basically your linear regression fit is represented by y hat x beta. So y hat is your linear regression model, and this will give you the predicted values. So predicted values are equal to the product of your feature matrix X. The feature matrix X will be a M cross N matrix, and beta, that's your coefficient matrix. So if you multiply the feature matrix with the coefficient matrix, okay, you will get the predictions. That is your y hat. Okay, so these are predictions from your model, and this essentially itself is a linear regression model, right? So to get the optimal values of the model coefficients, this is the operation you need to do. Okay, you'll take the transpose of your feature matrix and multiply with the original feature matrix. So that's what is the x transpose x, and then for that product you'll take the inverse. So you take the inverse of x transpose x and then again multiply with the transpose of x, and finally multiply with your target value. So what is y? This is your actual target. So x is your feature matrix and y is your target. So this entire back-to-back matrix multiplication will give you the optimal values of the model coefficients. Now where is the problem? So if your data set contains, if your feature matrix contains lot of collinear features, okay, a lot of features which are highly correlated to each other. Let's say x3 and x4 are highly correlated to x1 and x2. Then your feature matrix contains high degree of multicollinearity. And if that happens, then the determinant of this x transpose x, okay, because we have to take the inverse of x transpose x, if you see. So the determinant of x transpose x will be close to 0. And so you cannot compute the inverse of x transpose x, which means you cannot compute the beta coefficients, which means again that you cannot create your linear regression model. That process will fail and actually you will get an error. So if the determinant is also very close to 0, it's still called as ill conditioned. Okay, you might need to make some changes. So let me take a couple of examples here. So I have a very similar matrix, 1, 2 and 2, 4. If you see, the second row is just the multiple of the first row. So if any column is a multiple of existing columns or a linear combination of the existing columns, it will lead to multicollinearity. Same applies for the rows. If one of the rows is a linear combination of the previous rows or a multiple of one of the rows or just addition or a ratio or some factor of some of the existing rows, again that will lead to multicollinearity. So it's not only because of the columns, but you can have repeated data points leading to multicollinearity as well. And you can see that the determinant is almost close to 0. So if I try to do that inverse, I'm getting this error. Error says your matrix is a singular matrix and we cannot do the inversion. Okay. So, and what error is being raised? The linear algebra error. So that is the actual error. Okay. If you try to do this without the try except block, you will be able to see the actual error message. So let me show that. Yeah. So this is the linear algebra error singular matrix, which I'm just capturing here. So here if you see, instead of 2, I have got something very close to 2. Instead of 4, I've got something very close to 4. Again, if you see, the second column is a multiple of the first column. So technically this is still a case of multicollinearity, and I'm indeed getting the determinant close to 0. Okay. So here also your matrix is non-invertible. So the same error you are getting. Okay. Similarly, there can be a scenario where the determinant may not be exactly equal to 0. It might be a number which is very, very small. Let's say the value of the determinant is 10 to the power of minus 14 or minus 15, not exactly 0. In that case, the inverse will have very large values because the determinant goes in the denominator while calculation of the inverse. Okay. So the determinant is not exactly 0, but very, very, very close to 0. Then the inverse can explode by having very, very large values. And that numerical instability, okay, also indicates that your matrix is technically not invertible. You should not be relying on such inverse. Okay, such an inverse is still not reliable. Although it may not give you an error in calculation, but that output is not reliable. Okay, so let me summarize what all we have discussed. So in this entire video, we have seen the matrix multiplication, addition operations. Also in this notebook, we have seen how do we calculate the determinants and the inverse, and we have tried to connect them with machine learning and some of the pitfalls. Now there are approaches in machine learning like regularization where we can still tackle scenarios which have high degree of multicollinearity, especially using the ridge regression that we will see in the subsequent discussions in this video series. So ridge regression can handle multicollinearity problem, and if you want an approximate inverse, that's what we call as pseudo inverses. So there are algorithms which can calculate an approximate inverse rather than the actual inverse which is being calculated by your linear algebra DET determinant function. Okay. So sometimes the pseudo inverses also work well. Okay. So in the next video, we'll talk about the rank, the linear independence, and how do these relate to the matrix invertibility. And then we will also use matrix concept to solve a system of linear equations. That's it for this video. See you in the next one. And make sure to like and subscribe for more such content. Thank you.